Okay, so the lesson today is about something called continuity. It's fairly intuitive. There's one kind of scary theorem in here that I'm going to go through very carefully, but the rest of it makes a lot of logical sense. Okay, so we'll talk about continuity. We'll talk about properties of continuity. We're going to talk about what's commonly known as IVT. There's a rule in calculus. If a theorem has its own name, it's really important. Okay, so we'll talk a little bit about that. It sounds scary. It's not. It's real simple. It's very logical. And then this weekend, try to be a better listener for your friends. Okay? You know what I'm saying?
At least you're listening. See how I do that? Nobody else responded. Glad you were focused.
Okay, so what does it mean to be continuous? Say again?
Not discontinuous.
Not discontinuous. Good. What's a dog? Something that's not a dog. I mean, it's not a false statement, but what does it mean? Go. You don't have to raise your hand.
Consistent,
Keep going.
like it keeps going.
Okay, can you give me an example of something that's continuous?
Going to school. You have to come back every Monday.
Okay. If we look at a domain range, that is a true statement, right? So what would the domain of that function be?
So, no domains are. Infinite.
Oh, you're not going to go to school till you die?
I think
No. I'm talking about your example of going to school. What's your domain for school? When do you start?
Monday.
Go back further. Did you go to preschool?
I didn't go.
Okay, so preschool through college, and then depending on how far, if you go to college, how far you want to go with that. Maybe you want to go and get a couple master's degrees. Maybe you want to get a PhD. I don't know why you would want to do something insane like that, but I don't know what your future goals are. We haven't talked about it yet, but okay, good. So in that point, it is a continuous function because you're always going to school. If you look at that thing, is it true over your entire lifespan? Hopefully not, because I wouldn't wish that on my worst enemy. Correct. You weren't going to school right out of the womb, and you're probably not going to go to school after you're 20-something years old. Okay, good. Make sense? Continuous. Goes on forever, never stops. Based on a certain range. How do you know if a function is continuous? Is the function x squared continuous?
Yeah.
Why? Keeps going. Never stops. Keeps going in the left direction, keeps going in the right direction. Is a line continuous? Yes. Is a piecewise function continuous? Sometimes. Ooh, that's a little shaky. We don't like sometimes in math. Okay, so how, as it applies to math, we're going to use the KISS method here. We all know what the KISS method is, right? No? Keep it simple, stupid? Okay, we're going to keep it simple. How do you know if a function is continuous? Let's suppose you're sitting at the dinner table with your 7-year-old brother, and he asks you, hey, what's a continuous function? Number one, you'd wonder what's wrong with your 7-year-old brother. But number two, you want to explain it to a 7-year-old. How do you explain a function is continuous to a 7-year-old?
No breaks. No breaks in line.
Love it. Keep going.
No holes, no discontinuities.
Is a 7-year-old going to be able to handle the word discontinuity?
Maybe if he's asking about this, probably.
Well, maybe. Anything else? So you use the word no holes, right? If a function has a hole, it's discontinuous, right? Okay. What else would cause a discontinuity?
Breaking the graph, so from one to four, there wasn't
Okay, so we're going to look at three things that cause what's called a discontinuity. Spots where it's not continuous. Okay, so that's the same thing. They're not continuous discontinuity. Is effective. Simplistic terms, and this is where we're using the KISS method, what I want you to do is continually use the following idea, and that is, can you draw this graph without picking up your pencil? Remember those puzzles you see where it's that house-looking thing? Can you trace this without picking up your pencil? If you can, win a prize, that kind of graph? Yeah. The same idea applies here. Can you draw the graph of x squared without picking up your pencil? That wasn't a rhetorical question. Yes. Can you draw the graph of a line without picking up your pencil? Yes. If you can, then it's a continuous function. So what I would love to see is when you attack these problems, the first thing you do is use this KISS method. Can I draw this graph without picking up my pencil? If the answer is yes, you've got a continuous function. If the answer is no, then you need to figure out why is this graph discontinuous. And we've hit some of them already. In fact, I've listed them at the bottom. 3 methods that cause discontinuity: holes, jumps, and gaps. Now, this is the important part that I want to go over in depth, and then everything else is gonna be fairly easy. This is what's called the formal definition of continuity. You are going to be asked, and I'm going to tell you right now. Here's a question on the test on Thursday. I'm going to give you a function, and I'm going to ask you to use the formal definition of continuity to determine if the function is continuous or not. 3 parts. Is the function defined everywhere? Does it have a limit? And does the limit match the definition? Okay. Now that seems a little confusing. I have some examples, and we'll talk about why these following examples are discontinuous according to that formal definition. In order for a function to be continuous, all 3 scenarios have to be met. Are you with me? Great. So, here's our first example of a discontinuity. Commonly called the hole. The fancy technical term is a removable discontinuity. You've removed part of the graph and created a hole. Okay? So, let's talk about the 3 parts. Is the function defined everywhere? No. Done. As soon as one of those 3 things are violated, the function is no longer discontinuous. I think you all see that that function is clearly discontinuous, but I'm going to ask you why. We got to number 1. The function is not defined everywhere, therefore it is discontinuous. And we're going to go back to the idea of this funky point. So in the definition, notice they refer to this point as A. At this weird point, or this funky point A, is the function defined. This removable discontinuity is not defined at 1. Therefore, it's discontinuous at 1. Does it have a limit at 1?
Yes.
It does. What's the limit as g of x? What's the limit of g of x as x approaches 1? 2. Good. Outstanding. Does the answer from part 1 match part 2? Well, that's a stupid statement because part 1 was false. There isn't a value. Therefore, it is discontinuous. Second discontinuity, jump discontinuity. You see these commonly with piecewise functions. Looking at the graph, you can see a funky point at -2. So, step 1, is the function defined at -2? Yes or no? Yes. In fact, what is f of -2? 2. Good. Does it have a limit at -2? No, because right-hand limit doesn't match left-hand limit. Done. It is discontinuous at -2. And then the third one is called an infinite discontinuity. You know that is an asymptote. And that's just a train wreck. It violates everything. It's not defined at the value, it doesn't have a limit at the value, and the limit and the value of the function don't match. So infinite discontinuities are a train wreck. But again, as you approach these problems, I would love to see you say to yourself, self, can I draw that red picture without picking up my pencil? I develop random accents, I don't know why. Can you draw that red picture without picking up the pencil? The answer is no, so it's discontinuous. Okay, that's it. Those are the only three ways you're going to get a discontinuity. Now, you will see some functions that get saucy and throw more than one of them in there. You could have a function that has an asymptote, and a jump, and even a hole involved. But there's no other way to get a discontinuity in a function. Okay. Problems with that? Good. The biggest thing to get out of this is the formal definition of discontinuity. You have to discuss all three parts. Does it have a value? Does it have a limit? Does the value match the limit? And you'll get some of this practice when you do the homework. Okay. We know this already. This is just a rehashing of this guy. Left hand limit must match right hand limit. I'm going to go through this quickly because it's the same as we did with limits. If you have two continuous functions and you add them, they stay continuous. You subtract two continuous functions, they stay continuous, etc., etc. So we've got the same old product, well, sum, difference, multiplying by a constant, product, and then dividing is okay as long as G doesn't cause any problems, because we talk about those rational functions, and sometimes rational functions will generate asymptotes which causes problems. This is big. When you start attacking these problems and you're asked a simple question, is this function continuous? If you can identify that function as being a polynomial, you're done. Because, as it said, oh, watch, I spent some time on this. Okay, Ray, look up. You ready? Yeah, yeah. Don't look at me, look at the screen. Now I gotta do it again. Hold on. It took me hours to figure out. Yeah, I know. Thank you, thank you. Nothing but the best for you guys. Oh, wait. Yeah. Double wave. You won't get that in every class, kids. You're sitting in Everett's class, he's not double waving. And he's probably writing it on the board in crappy handwriting. Sure, if you'd like to see that again, I can do that one more time. Because it's Friday, I get it. There we go. Well, since I made that blue part a wave, I guess I should ask the question, what's a polynomial, Jack? Does that help?
Nobody wants to say it didn't help them. They don't want to hurt your feelings. I'll say I have no clue what you're thinking
Okay. It's easier. Is it safe to assume you all know what a polynomial is? It's not a rational function. Okay, you're not dividing by x minus 2 or something like that. All the exponents are integral values, positive integral values. Okay, so x to the 5th minus 3x to the 4th, blah, blah, blah. Those are all polynomials. As soon as you see that, you know it's continuous. Then the last part is we talk about composite functions. But composite functions are easy. Number one, you know what a composite function is already. And number two, if you take a continuous function and you stick it in another continuous function, it stays continuous. It's pretty hard to screw up continuity once you have it. Okay, let's skip this. I mean, you all know that tangent has asymptotes, therefore it's discontinuous. Great, let's move on. Intermediate value theorem. As I said, if it has its own name, it's important. But the intermediate value theorem is very easy. Okay. Andrew, any idea how big you were when you were born? approximately, what, 22 inches, 20,
Sure.
you wanna go with 20? How tall are you now?
5'7".
5'7", beautiful. So, and when you were 3 years old, you were about how tall? Guesstimate just for discussion purposes. Okay? Does it make logical sense that if Andrew was 20 inches long when he was born, and now he's 5'7", that he has covered every single height between 22 inches and 5'7" in the time span of, what are you, 17, 18? 17 years. Okay, does that make sense? He didn't wake up one morning and go from being 3'2" to being 3'6". Somewhere along the line you have to cover those distances. Does that statement make sense? Yeah. So Andrew's growth is a continuous function. There's no gaps in his growth. He didn't lose any distance. We could go back and track his record and find at some point in time he was 4'1". At some point in time he was 2'6". At some point he was 5'5". Does that make sense? What it means is that from 22 inches to 5'7", he has covered every possible height along the way. The intermediate value theorem says that if it's a continuous function, like his height, if you know your starting point and your ending point, he must have hit every height along the way. So how do we apply that to math? Well, most commonly, the intermediate value theorem is used to find distances when you don't know how to find the distance or the value. Okay, so what do I know here? I know if I look at that curve, I know f of a equals 1, and I know f of b equals 5, and it's a continuous function. You must establish it's continuous. That means that somewhere along the line I have to cross 2, or 3, as I mentioned in quotes. Where is the intermediate value theorem most commonly used? It's most commonly used to find zeros of a function. Because if I know that it's positive at one point and negative at another, it's got to cross 0 somewhere along the way. So that's basically a summary of Andrew's height. So I have an example here. Here's an example. I have a cubic function, and I have a value from 0 to 1. I want to use the intermediate value theorem to prove that if I graph that function, go ahead and graph it, either on your calculator, decimals, whatever you got, graph it. We're going to prove mathematically that that graph crosses the x-axis. In other words, it has a 0 between the values of 0 and 1. Without actually calculating where that happens. I don't care where it happens. I just want to prove that it does happen. So while you're graphing it, I'll do a little bit of work here. Question number 1. Is the function continuous? Yes or no?
Yes.
How do you know? It's a polynomial. Beautiful. Polynomial. Check. Okay, that's the first part. That's what's called the hypothesis of the theorem, the first part of the theorem. We've established that. Muy importante, see? Okay. By the way, you have a graph now. Are we going to get does it cross 0 between 0 and 1? Yes? Well, let's find out. What's f of 0? Negative 1. What's f of 1? 2. Plug and chug. What does that mean? I start at 0, which is at negative 1. I'm below the x-axis. I end above the x-axis. I can't get from negative 1 to 2 without picking up my pencil, without crossing the x-axis. I have to cross the x-axis somewhere. Okay, that's all the intermediate value theorem does for us. It shows us that there's a value there. Now, you could go on and say, okay, well, where does that happen? Well, that's a different problem. That's taking this and setting it equal to 0 and solving, which I don't care about right now. All I want to be able to do is show that it does cross the x-axis. So, by IVT, f of some value must equal 0. IVT only works if you establish that idea. If it's not a polynomial function, it screws everything. Sorry, I didn't mean that. If it's not a continuous function, it screws all that up. So you start the problem by saying, yes, this is continuous because of, and most commonly it's going to be because it's a polynomial. Then you go on and find the starting point, find the ending point, and then end with a summary. Okay. How do I know there's a 0 there? Because it starts at a negative value and goes to a positive value. Okay. Good? Put that to dead. Yep. Oh, look, I did all the work already. We're done. So again, use the KISS method on this section. You're going to have to do a little bit of algebra when you're grinding out the problems, but for the most part, the concepts should be fairly logical. Don't forget those 3 parts. Reiterating, on Tuesday, we will go over the day 9 homework, which we haven't talked about yet. We'll talk about the day 10 homework. I'll give you some time to work on a couple review problems. We'll go over the review problems. We're done. Thursday, when you come in, we'll start with the test. So again, if you're concerned about being able to get all those review problems done, then start knocking out a couple of them over the weekend or before Tuesday. Yes, go on. Go. Where are we headed? I'm sorry, where?
ISU.
Oh. What's going on at ISU? Is it a big tournament? It's not the state tournament yet, is it?